transformation of variable parts. Okay, so remember what we did there. We basically have a quantitative y variable, right, and a quantitative and binary x's, as usual. But the assumptions are violated, or the plot doesn't follow a linear pattern. So we want to see if we can transform either the y or the x's to make it more linear. And that's what this whole section's about. And then the first few questions on the exam are about that. Okay, so let's look at this. And this first question is almost too easy. Don't be insulted if you see a too easy question. So match the scatter plots in the top row with their corresponding residual plots in the bottom row. All right, so I think that, let me go a little. This is almost too easy. You might think there's a trick to it. There's not. It's just these residual, on here is just the errors in y, and here's your y variable. So all we did was basically get rid of the tilt there. So you can see this one that has this fan shape like this is going to match with this one. That's plot C. This one is going to be plot, which one? Plot A, and this is plot B. And why does this look so, this does not look right. Let me just see. Let me make it, just looks, see if we can get it clearer for you guys. Okay. Maybe that's a little better. Okay, so any questions on that? How that matched up? Okay, now one of the assumptions needed to use a linear model for inference is that the variability of the y's should be the same across all values of x. Which scatter plot seriously violates that assumption? Circle all that apply. You know what we mean by the variability of the y. For any x, you're going to get y's that are variable. You know, in any little, like here's the variability. You know, the y's are varying. It's basically the width for any of the strip. And do you see how for plot C, the width, it seriously violates that? Because you can see that as x gets bigger, the variability of the y's get really bigger. Whereas here, they don't. You know, the variability, there's a little bit of a width here. It's about the same here and the same here. Does everybody understand that? That's all we're talking about. That's pretty easy. Okay. Now, all right, so what's the next one say? Which of the scatter plots do not show a linear trend? Maybe I should say the variability of the y's goes up as x goes up for the C. Whereas the other ones, it's pretty constant. All right, now which of the scatter plots do not show a linear trend? Which do not show a linear trend? Well, that's pretty easy. This one does show a linear trend. You know, it just has it violates the homoscedasticity assumption. But look at these. These show curvilinear, right? So those are the two. That's the answer. All right, next one. Suppose you'd like to do a linear regression, but your scatter plot is not close to linear. So you see that, and so you look at the histograms. Remember, when it's not close to linear, one of the things we do is we look at the histograms of the y's and the x's, and you see that the histogram of the y variable is left skewed. It has a long left-hand tail, so it looks like that. A long left-hand tail that's skewed to the left. All right? So now which of these transformations would help correct that? What you want to do is you want to make it more normal looking. So basically, which transformations would be possible candidates for doing that? Think about this. If this was like 0 to 10, we want to stretch out this side more. So if this was 10, the end point, it would stretch all the way. If you squared it, it would stretch all the way to 100, whereas 0 would stay fixed, 1 would just stay at 1, 5 would just go to 25, so it would make it more normal. So that would be so these three. In y cubed would do an even more dramatic transformation, remember, these are all positive. We're assuming these are all positive. So let's just say 0 to something. And e to the y would be even more dramatic. Okay, so these. How about these? What would these be applied to? These would be applied if it's right skewed, right? If it's right skewed, remember like our animal weights, when we had dinosaurs in there, to even see the mammals, the little mammals, when we had these giant dinosaurs out here, the weights, we had to change, we did a log transformation. We could have done a square root, but that's not as dramatic, or this would be even more dramatic, but would also reverse direction. So this is a right skewed, and you want to bring these in. So basically, we're looking at the exponents when we do a log. And we've done a lot of log transformations. And which directs? So we'd go from the square root is the first one we try. That's not as dramatic. Then the log of y, and then 1 over y. But we haven't really looked at that much. Basically, we haven't looked at these two. So the graphs that I'll show you will be those. But that is something that could be done. All right, so any questions on that? Right skewed just means long right-hand tail, left skewed long left-hand tail. And all our data that we've been looking at is positive. You can't take logs of a negative number or the square roots. So they're all positive, what we've been looking at. All right, so let's look at some data here. And please stop me if you have any question at all, or if I make a mistake, stop me. Even if it's a really silly mistake and you know it's silly, just it will help everybody out if you correct me. Okay? And I'll give you an extra credit point personally on your exam if you correct me and find a mistake during the review. All right. So now, what's this about? So this question pertains to the area in kilometers squared, and the number of mammal species for 13 islands in Southeast Asia. How does the size of the island predict the number of species on the island? So here's just, without any transformations, here's your area of the island, the size of the island on your x-axis. This is area. And here's the number of species of these mammals on the y. And notice how most of the islands are all squished together here. You can't even really see them. You can see these big islands that are Borneo, Sumatra, and Java, the ones you've heard of. But these little ones you can barely see. They're all squished together in the corner. And look how skewed this area of the, this histogram of the area is. So this is the histogram of the x right here, the area. I want to transform this x variable to make the histogram more normal looking. And so which transformation should I try? Circle all that would work. That's what we just said. Look, we have this right-hand tail here. Think of it this long. And we want to squish these in so we want to change the scale so that these little animals, these little islands can appear, and so we can see what's going on there. Right now, it's just like a giant point there. We can't distinguish them. So what we want to do is which transformations? The square root or the log. All right? Now, I tried both of them. I tried one of the transformations, and it was a step in the right direction, but it didn't go far enough. And I tried another one, and it worked much better. Which ones did I try? So this is just what we went over in the last page. This one didn't work. You know, this is your first step. So this is the square root that helped compared to this, but this did a lot better job. This was more drastic, and this is the log. Okay? Questions so far? Now, all right. Now, below is the scatter plot. I logged both variables. So here's log of area. And this is log of area, and this is the log of the species, natural log of both. And it will show up a lot better when you look on your own exam, when you look to online Kappa. But now the islands show up. I can't even see what they are, though. Let me see if I can zoom in, if I can see what they are. Okay, so that's Borneo, that's Java, All right, so now you can see them better. I didn't label them all. So I say that, okay, so here's your regression equation, and here's the standard deviation of the errors. And where species is the number of mammal species, this is the log of species on each island, and area is the area of each island. Okay, now use, so it's the log of the area and the log of the species, and use the regression equation to predict for that one, for that island. So which one is it? So that's this one. Okay, let's zoom out so we can look at this again. All right, so that's the one we're going to make a prediction for, and it has, its area is 450, so all we're going to do is put area in there. It's super easy, and just solve for our log species. Okay, so the log of the number of species is what? That's just going to be 1.6 plus 0.23 times the log of 450. And I did that, and it says round, what does it say? Round to one decimal place, and to one decimal place, that's what I got, 3.0. And you can check that it kind of doesn't look about right. It lines up with 3, yeah. And the log of 450 is probably about, must be about 6. All right, so this looks right. You can check, at least make sure it's in the right ballpark. You can't check if you know, just make sure you did it pretty well. And then, so now we just want, okay, so what does it predict for species? So this was the log, so we just anti-log it, exponentiate it, and this is easy. It's e to the 3.0. And you can always use your rounded answers on the exam, or if you want to leave your digits in the calculator, you can do that too. Either way, it's fine. This is kind of easier to grade, but it's fine if you want to leave it in there. Okay, and here you get 20 rounded. All right. I'm not going to take off for the rounding, you know, if you're just off a little bit, like I'm not a computer. We're grading these by hand. So, of course, if we follow your work, of course, we're not going to, you can use that. You don't have to keep all the digits in your calculator if you don't want to. Now, so now the question is we just want to build a confidence interval, and you have to be a little careful here. We're going to be using this to build the confidence interval, and it's a 95% confidence interval. So we're going to be adding error bars based on the normal curve, which looks like this, and has 95% in the middle, corresponds to z-scores between, this is what we're going to be, between 1.96 and negative 1.96, but it's fine if you do 2 and negative 2, and it's actually easier to grade, and you can keep track of it better in your head. So that's going to be the critical value for z that you'll be using, would just be 2. And so you're fine. So what do we want to do? For the species, okay, now this right here goes with the log of species, so we're going to have to do it in 2 steps. Your final answer should be a confidence interval for species right in here, not log species. All right, so now you can't go directly to this answer. You have to do it in 2 steps. So the first step, remember, is the confidence interval. This error goes with this equation. So it's the confidence interval for the log of the species. Okay, log of the number of species is what we're going to do first. And that's going to be this estimate. That's our point estimate. And then we're just going to put a margin of error around it. You know, we're just going to say this is an estimate, and so we're going to say plus or minus. Remember, this is, we're estimating this using this. Okay, so plus or minus what? 2 times 0.3, right? 0.2. All right, so this is for the log. We have 3 minus 0.4, right, down to 2.6, all the way to 3 plus 0.4, and so that's it. But don't put that in here. That's not your answer, right? The question asks for the confidence interval for the species, not the log. So what do we have to do? We just have to anti-log that. So it's e to the 2.6 to e to the 3.4. Okay, whatever that is. And I, do I have my calculator here? Yep. All right, so we'll just do e to the 2.6. So that's, you can round to 13.5. Is that what it said, 1 decimal place? And then e to the what? 3.4. And that'll be 30. We'll round to 1 decimal place, and it's 30. So that's our answer. Questions? And now check your answer. How are you supposed to check this? Well, what are we supposed to do? We're saying 20, so we're putting we're putting a confidence interval around the number, around this 20. And you can't just, it's not going to be in the middle of that. You know, it's this our log species is in the middle of this. So, that, you know, so 3 is the average of these two. But 20 is not going to be the average of these two. Instead, it's the geometric mean. It's not the arithmetic mean. So to check your answer, you just go 13.5 times 30 and make sure you get that. Make sure it's the geometric mean. Okay? So we can do that. You know, I'm just going to say 13.5, you know, within rounding error. Yeah, it's good. Just to make sure you're not really far off. Okay, questions on any of this? Now, this is very similar. You know, we're going to move on to logistic regression, which is different from this. We're going to be using, you know, similar. We're going to be using log transformations, but they're not on the variable itself. We're looking at the log odds because the variable itself, the y variable, is a 0, 1 variable in log. So we're doing logistic regression, which is which is something very different. It's when you have a model where you're trying to predict a 0, 1 y variable, and so that's why we can't just do our usual linear regression, but we transform. You know, because how are you going to predict zeros and ones? We don't have a quantitative y, so it's really the probability of getting a 0 or a 1, and we see that's an S-shaped curve, so we transform that to the we're in this range here. You know, we have 3 forms for this equation. It's this, or here's a linear, and the linear is in the log odds. Okay, so let's just first start up here, and for each of the following, is it appropriate to use logistic regression? Circle yes or no. Is it appropriate or not? So basically, if predicting surviving into your 90s based on diet and exercise, can you code that? Is it yes or no? Did the person survive into the 90s or not? Yes or no answer. It's a 0, 1 variable. Survive could be 1, not survive 0. So that's yes. Predicting age at death. If we're predicting a y variable that's the age, that's a quantitative variable. It's not, did you live past 90? It's how old was the person when they died? So we can't. Same with income. Predicting income from education. If I said predicting whether somebody's going to be a billionaire based on their education, then it is a yes-no variable. But predicting income, no. We'd probably want to do a log transform, but that's different. We're not using logistic regression. Whenever you predict something like income, you would want to probably do a log transform because income is so skewed to the right. But that would not be logistic regression. That's just transforming a variable. This is not a 0, 1 variable. So you can't do logistic regression. Predicting the score on this exam from our study, again, no. But predicting whether you get an A or not on this exam, yes. That's a 0, 1 variable. Understand? All right. It's what you're predicting has to be 0, 1. The X can be either 0, 1 or quantitative. All right. So, true or false? The logistic regression model only handles y values that can be coded as zeros and ones. Absolutely true. All right. Now, so to get you, I wanted you to just understand how to go from probability to odds to log odds. So I gave you different, here it's just filling in charts given, here you're given the odds and you have to fill in the other three. Here you're given a p-value, probability, and you have to fill in the other ones. Here you're giving the log odds. So you should be able to go back and forth. And here I'm asking you to express it as a fraction. So just remember what? What is odds? You should know what odds is. It's just the probability of success over the probability of failure, right? And P, the probability, is odds over 1 plus odds. So that's basically what you'll be using. All right, probably these are the easiest ones for you to do, like starting a probability maybe, or this one might be a little tougher. I'm not sure, but whichever one's easiest, just start there. All right, so let's try this one. 99, if the P is 99 out of 100, then the 1 minus P, of course, is 1 over 100. And then your odds are what? P over 1 minus P are 99 to 1 odds. Okay? Now you can look at this one. Here you have 1 to 99 odds, right? 1 to 99. So you can think of it as the total outcomes, probability. This is the success probabilities. These are the number of successes. These are the number of failures. And if you add them together, it would be the total. So you could say probability of success is 1 out of 100, and this is 90. This is 1 out of 100, and this is 99 out of 100. Or you could use this formula. It's the same thing. Like if you could do this formula and just say odds over 1 plus odds. Whoa, so sorry. Why did it do that? Okay, so we could do that, and it would be, you'd get the same answer. So 1 divided by 99, right? And then you can divide that. I'm just doing odds over 1 plus odds. And I get 1 out of 100 as well. But I asked you to put it in a fraction. So it's the same thing. All right, any questions so far about that? Now, what should we do here? Okay, what's this one say? 1/10, so this would be 9/10, and then the odds are 1 to 9. Here, 1/10, 9/10, right? P and 1 minus P, and 9 to 1 odds. And to figure out these, you're going to have to do what? You're going to have to use your calculator for that. So let's figure this out first. Here we have the log odds, right? So now we just want to get the odds. So it's e to the 0, and it's just 1. You can write it 1 over 1 if you like, but it's 1. Okay? And now, to get P, you could say 1 over 2, or you could think, okay, there's a total of 2 outcomes, 1 success and 1 failure. And, we've looked at this so many times, that a probability of 0.5 is 50-50 or 1 to 1 odds, and the log odds of 0. Those are all the same. So now for these, you have to have your calculator, so let's look at this. So what's the log of 99? And I said use round to 2 decimal places, so this would be 4.6. And then you should know the reciprocal would be negative 4.6. And what's the log of 9? So that's 2.2, and the reciprocal is negative 2.2. So that's pretty standard. And any questions? All right, now we're going to, this is really important. The logistic regression model has three equivalent forms represented by these three graphs. Now the probability form, you should recognize, is this S-shaped curve that goes, it's bound, probability only goes between 0 and 1, and this is bounded like this. So this one is B, and it goes from 0 to 1 like that. The odds form is an exponential curve like this. So this is the odds form, and the log odds is finally this linear equation here. So that's what we've got here, and so we have B, this one C. In fact, we should probably write this down. Okay, so this one is the one that we are getting parameter estimates for, and it's the log odds. The log of P over 1 minus P is equal to some intercept plus a slope times X. That's just a linear equation there. That's our log odds. This one right here, when we exponentiate that, this is the odds, so that's P over 1 minus P. P over 1 minus P, or the odds, is equal to E, when you anti-log that, E to the beta naught plus beta 1x, right? So you can see how this slope here, this slope that says if you go over 1 in the x direction, you go up B1, that one becomes here, becomes what? When you go over 1 in the x direction, if you add 1 to this, what's going to happen? You're going to be multiplying. So you're adding here, but that would be e to the beta naught times e to the b1x. This is going to be e to the slope. So if you go over 1 in x, your odds, that's the odds ratio, increase by a multiplicative factor of e to the b1. So for example, let's say this was 3, so we had a steep line here. Then we'd have a steep upward curve here. You'd say, okay, if you went over 1 in the x, you'd go up by 3. But if you went over another one, now you're going up by not 3 again, but it's, if you go over 2, it's going to be a multiplicative factor. So you'd be going up 9, then 27. So a difference of 3 would take you up 27, rather than here, a difference of 3 would just take you up 3 plus 3 plus 3. That's why it keeps getting steeper. It's increasing exponentially, and that's called the odds ratio. The odds ratio is it's a constant multiplicative factor, right? It's a constant multiplicative factor. The slope keeps getting steeper and steeper. And here it's a constant additive factor, so the slope stays the same. And here there is no constant slope in terms of multiplication or addition. I mean, it more gradually increases, then it really steeply increases, and then it gradually increases again. So the odds ratio is used to describe how this slope is changing, and this is used to describe how this slope is changing additively. So that's, now we've got to get the equation for this one. So the equation for this one is odds over 1 plus odds. Right, this is P over 1 plus P. Excuse me, P is equal to odds over 1 plus odds, sorry. So our equation for this one is P is equal to e to the beta naught plus beta 1x over 1 plus e to the beta naught plus beta 1x. All right? Maybe it's easier to read it if I do that. Okay, so probabilities range from 0 to 1. Of course, you know that. I'm supposed to say what they range from here, 0 to 1. And odds range from what? They range from 0. This is 0 to 1, 0 to all the way up to positive infinity. It goes all the way up. can see that here. And you can see that the log odds are going to go from negative infinity to positive infinity. So they go up to positive infinity and down to negative infinity. All right, so that's the idea. And any questions? So now we're going to do some, analyze some data with logistic regression. And this was a survey. I asked you the same questions and a lot more, some more interesting ones actually, on the survey that I just gave you, and I combined it with Stat 100. And so there's some interesting data there. But here's 3 questions that I think I did ask you guys. Let's look at this. This was on a different Stat 100 survey. I can't remember what year it was from. But 893 students anonymously answered these 3 questions. Have you yourself ever happened to try a same-sex experience? 0 was no or yes. 0 is no, and 1 is yes. So this is, we're going to be predicting this. We're going to try to predict whether somebody has tried gay sex based on gender, which is this 0-1 variable, and based on how they rated how religious they were. So this is quantitative variable. 1 means not at all religious, and 10 means extremely religious. So I wanted to see if that was a predictor of whether people said they had responded that they had or had not had gay sex. So here's below is the output from logistic regression model predicting the probability of trying gay sex from gender and religious ratings. Okay, so it's self-reported. It's anonymous and self-reported. It's what people said they do. But hopefully people are telling the truth here. Okay, but we're just predicting what they say. We're predicting whether they said they had gay sex. We can't really, sometimes people lie about stuff like this. Come on. Oh, I don't know why it's having so much trouble today with focusing. All right, so let's look at this. Now we can do this, we have a big data set, so a chi-square test is a good, going to work here, and this might have been a modified chi-square test, but at any rate, this is, it's very close to a real chi-square test here. And what are we given here? So how many degrees of freedom would we have for the chi-square test? Well, the degrees of freedom are equal to the number of parameters minus 1. It's also equal to the number of x's, because one of the parameters, you have 3 parameters here, including the intercept. You have an intercept, that's one of the parameters we're estimating, so this is 3 parameters. Another way you can think of it is 2 x's, so the degrees of freedom are 2. You have an x1 and an x2 and an intercept. Like this is an x1 and an x2. Questions on that? All right. Now, what if I didn't give you the p-value here, and I just wanted you to look at a chi-square table? We could do that. Let's say I gave you the one in the book. So you know there's lots of chi-square curves depending on the degrees of freedom. So here we want the one with 2 degrees of freedom, so we'd just be focusing on here. And this gives you the critical values for the different cutoffs. Okay, so we could compare our chi-square statistic of the one we got, our chi-square, which was pretty big, equal to 12.23. And let's see, and we're given a p-value of 0.21%. Let's see if that agrees with what we'd find here. So we just look at where our chi-square compares to these 2 critical values. And you can see it's it's in between 9.21 and 13.82. So that means our p-value is going to be less than 1%. It's further out than 1% on the tail, but not as far as 0.1%. And our p-value is closer to 0.1 than 1%. So it agrees with that. So a question I could give you, if I blank that out, is I could ask you which range it's in. You know, whether it's in between 0.1 and 1%, between 1 and 5%, et cetera. Okay, and you could read that off. So you would conclude that's a small p. The probability that that would happen just by the luck of the draw is very small. Remember, this we'd expect, with 2 degrees of freedom, we'd expect when the null is true, when the null is true, when those slopes are both 0, we're testing in this overall right here, we're testing this overall. We're saying that the null is that both these slopes are 0 in the population, and in our sample we happen to see an effect. And we're rejecting that. We're rejecting that. We're saying if that was true, the likelihood is only 0.21%. All right, so we know at least one of them is significant, and now we can do tests on the individual slopes. Here I gave you could see that the religious slope is significant. It has a p-value very significant. So that, and now I'm asking you to calculate z to test the individual slope for gender. And I'm giving you that the null is always that the slope is equal to 0. And I'm saying, we could have a 2-sided alternative or a 1-sided. In this case, I'm saying I really didn't know which way it would go. And let's do a 2-sided alternative. And I really didn't. I didn't know whether men or women are more likely to have had gay sex. Okay, so this is the 2-sided alternative. And let's look at this. So this is your observed slope in your sample minus the expected, which is 0. So we're just saying 0.5052 divided by the standard error for the slope, which will be given to you 0.2432. And this turns out to be 2.08. So you could probably tell that it's going to be significant because between 2 and negative 2 is about 95%. This is a little bit bigger, so you can look at it. Is the p-value less than 5%? Yes. And between negative 2.08 and 2.08 is remember, we never use F or T tests for logistic regression. So let's look here, 2.08. So we can round it to like 96, let's say. 96, let's just round it to 96. I'm not asking you to do exactly. So that would be 96% in the middle. And so for a 2-sided test, it would be this tail, and that p-value is about 4%, so yes. If I did a 1-sided test, if I knew ahead of time that girls are more likely to say they've had gay, girls are just more likely in all the data most of the data I've collected to just try it occasionally, I guess. Just their sexuality seems to be a little bit more fluid. I always get data like this. I'll see what happens. I haven't looked at our data this semester, but this is saying that girls are more likely to have tried gay sex. All right, so now, and it's significant, and it's saying that given controlling for how religious they are. Oops, I just gave away this. Are females more or less likely to have tried gay sex than males, assuming their religious ratings are the same? So if they're for the same level of religion, are they more or less likely? How do I know it's more? Because they're coded, this is positive, right? The slope right here is positive, and females were coded as 1. If females were coded as 0, if I coded females as 0s, then this would be negative. This says as you change from 0 to 1, you're more likely, it's a positive, you're more likely to have said you had gay sex. All right, the higher the religious rating, what? the higher or lower the probability of having tried, assuming the same gender. So we're looking here, and you see the negative. So that means the higher the religious, the lower. And that agrees with what you would intuitively think, the probability of at least saying you had tried gay sex. All right, because in a lot of religions, it's taboo. Now, what's the log odds form of the logistic regression equation? So this is just reading that. It's given to you right here. So it's negative 1.918, 0.5052, and negative 0.1163. All right, so what's the odds ratio for the variable gender? Well, that's just going to be e to the slope for gender. So that's e to the 0.5052, which is about 1.66. This means that the odds of a female having gay sex is 1.66 times the odds of a male, assuming that their religious ratings are the same, because there's multiple regression. We're controlling for the other variables in the model. So now use this log odds model, which is right here that we have, to predict the log odds, and probabilities of trying gay sex for the two individuals in the table. So basically, I give you this is x1 and x2, right? And you can just fill x1 and x2 and just plug them in and get the log odds equation. So here, a male is coded as 0, so this is 0, right? And his religious rating is 0. I made it really easy. So this is what you have. The log is just that. The log odds is negative 1.918 plus 0 plus 0. And for females, what would it be? Well, females with a religious rating of 0. Well, here you have negative 1.918. Now you have to put a 1 in for females, so that would be plus 0.5052. But now she's not all religious, so that is negative 1.413. All right. So what's the odds now? So the odds, this is the log odds, so you just anti-log it, so it's e to the negative 1.918. And so that's the odds is 0.147. And here it's e to the negative 1.413. So the odds is 0.243. So she's more likely, both of these are more likely to not have tried gay sex than to have tried gay sex, which is no surprise. So the probability for men is what? P, this is odds over 1 plus odds. And this, all I did here was I said E anti-log this to get the odds. That's all I'm doing. Okay, so this is 1.147, and I got 0.128, and use as a decimal, unless I put a percent sign here, in which case you would say what? 12.8%. But I said round to 3 decimal places. I meant in the decimal here. I'd put a percent sign if I want you to change it to a percent. And this one is 0.243 over 1.243. So a woman's going to be more likely, and this was 0.196 or 19.6%. Okay, so this odds ratio should be 1.66. Let's just make sure it is. Going from the odds of, because it's just a 0-1 variable, so it's going to go, so the odds ratio, let's check that. Okay, the odds ratio we know is 1.66, and it's the same thing as 0.243 over 0.147. I just want to check to make sure that was right. Did I get 1.66? There's lots of ways you can make sure you didn't make a mistake. And so we can say 0.243 divided by 0.147 Yeah, within rounding error, yeah. So that's good. Any questions on that? All right. So I'll look through our survey data, and maybe if I find something interesting, I can put it on the test. And let's. So now we want to construct 95% confidence interval for the gender slope, and then for the odds ratio for gender. Okay, so for the gender slope, it's just a linear equation. So we're just gonna, we're just using this rounded 0.5. What on the previous page, it's almost 0.5. It's a little bit, yeah. I'm just making it rounded. There's too many digits here. Okay. So, all right. So what do you want to do? 90. Okay. So this is just going to be. You're just putting an error bar around 0.5, plus or minus, and it's 95%, so it's going to be 2 of these. So this is right, 0.5 plus or minus 0.48. That's the same as what? 0.5 minus 0.48 is 0.02, all the way to 0.5 plus 0.48, which is 0.98. Those are the same thing. This one's a 68% confidence interval. We forgot to multiply by 2. And this one got these backwards. 0.48, no. Okay, so that's what we have. Now we want to use this to make which one of the following, is not, be careful, 95% confidence interval. Which one is not? For the odds ratio. What is the odds ratio? The odds ratio is what? The gender, it's e to the slope. Let me just say odds ratio is e to the slope, so it's e to the 0.5. So we want to put some error bars around that. Now, I hope you see right away, it's not going to be that one. It's not going to be right. You can't, it's not going to be plus or minus anything. E to the 0.5, which is about 1.66, we saw that. It's not going to be, you can't put error bars around it like that. Look at the curve here. You're not going to, it's going to get changing more this direction than that direction. It's not going to be symmetrical. So you know this one's wrong. Let's see, make sure that all these agree with that, okay? So we just want to anti-log this, so e to the, this is the exact, this has to be right. If that's right, this one is just this anti-logging it. This is for the, we're just raising e to that. Okay, so this one for sure is right. This is the one that's, you should have answered. So now, and this one is, of course, right? We're just taking the endpoints. It's the same thing. This is the same thing. Is this one the same thing? Yes, this is the same thing. Instead of, what did I do? Instead of saying E, this is just E to the 0.5 minus that, right? Minus is the same thing as dividing and multiplying. This is a nice one because you can see when you take the square root of that, it's so easy to see why you take the square root of the endpoints of your interval, and you get, these two cancel out, and you get e to the slope again. So that's a nice one. So that one's good. And this one is just actually solving e to the, e to the 0 is 1, so this is just going to be a little bit bigger. So if you actually raised e to the, did it on your calculator, you can just do it. To the 0.02. See? All right. Any questions on that? So you can really see how e to the 0.5 is the geometric mean when you multiply those two together. All right, now our last, so this is just our last problem here. And it says a predictor of whether esophageal cancer has metastasized to the lymph nodes. Yes, no question. There's a lot of yes, no questions like this in medicine. Living or dying, does something spread, cancer spread, yes or no? Is the diameter of the tumor, all right? And here's a log odds equation predicting the probability of metastasis from the diameter of the tumor in centimeters from a hypothetical study of 200 patients. This isn't real data. I just made this up to have nice numbers for you guys to have on a test. All right. So now use the equation to estimate the odds and probability of metastasis for a tumor of 8 centimeters. So this is just easy here. Just show work. So we just plug 8 in there, and you're going to get your log odds is equal to -2 plus 0.5 times 8. 4 minus 2, so that's 2. So that's the log odds. Oh, I didn't ask you to do that. I just asked you to do the odds. Well, that's the first step. You have to do that first. Then to get the odds, we'd have to exponentiate both sides. So you get e squared is your answer. That would be the odds. And that's 7.39. And then to get your probability, remember, it's just odds over 1 plus odds. So 7.39 over 8.39, which is 0.88 or 88%. So that's a pretty big tumor and bad probability of getting metastasis. So how do the estimated odds change if the tumor increases by 1 centimeter? How does it change? Well, it changes by a multiplicative factor. Remember, the odds do. It's that exponential curve. So it's going to be multiplied. The odds would change by that, not this probability. The odds would change by by what? What's the odds ratio? The odds ratio is, we have to figure it out. Odds are multiplied by the odds ratio, which is e to the slope, which is e to the what? E to the 0.5. So it's that one. How does the probability of metastasis change if the tumor increases? Well, look at that. You're here. Just remember, you don't know. If you're here, right, it's going to change. If you're right in the middle here, it's going to change by a lot. If you're down here, and just think of it, a tiny little tumor, 1 centimeter difference isn't going to make much of a difference. Up here, you're dead already, or it's already metastasized. It can't get, see, it's flattened at 0 and 1. I mean, basically, it's not going to 1 centimeter going from a terrible, a huge tumor to 1 more centimeter, pretty much already metastasized. You know, it's not going to change much. It's going to change a lot in the middle. Here, of course, these are your odds, and it changed by a multiplicative factor. And this is just your regular slope. But this one, you can't say anything about this probability unless you knew what the size of the tumor was. Okay. So, or if you knew the odds. All you know is the odds ratio. If you knew the odds, you could say odds over 1 plus the odds. But all you know is the odds ratio. That's not going to help you. So, where are we? That's not enough information. Now, this last one is how big a tumor would give a 50%. Okay, somebody has a 50% probability of metastasis. How big a tumor would it be, or 60%? So I just want you to figure out for a 50% chance and a 60% chance, how big a tumor. So you have to go through all these steps here. And remember, the odds is p over 1 minus p. So this one's pretty easy. 0.5 is an odds of 1. 1-to-1 odds, 0.5 over 0.5. So the log odds is 0. Log of 1 is 0. And you can then we use this equation right here. That's all we're doing. All right, and we know that the log odds is 0. So we'll say 0 is equal to -2 plus 0.5 times the diameter, and just solve for the diameter. So the diameter here has to be what? 4, right? 4, half of 4 minus 2. All right, now let's do this one. So this one, 0.6, okay, 0.6 probability is what odds? 0.6 over 1 minus 0.6. So it's 3 to 2, or 1.5, you can say. 1.5 odds. And you'd have to take the log of 1.5. And I did, and I got that. It's the log of 1.5. And now you just solve again. Okay. So that's the answer. Any questions on this? So how are you going to study? You can get out early today. We're done with this. If you go to Compass, you'll see last semester's exam. And then another really important thing to do is the practice homework again. So anything you feel rusty on, and just because there'll be things on here that aren't things on your exam that weren't on these exams, right? Anything that's on the homework is fair, or you should be able to do too, or anything that's been on a practice exam. And also just, there's going to be slight variations. So if you want for the homework, tonight I'll put all of it under practice homework, so you can go back and do any homeworks you want with new variations. So I strongly recommend you just make sure that you are really, some of this can just be turned into muscle memory, and others of it will help you understand it. So just do a lot of variations on problems, and I think will help you understand it, and read over the summaries.